This next topic that we're going to consider is statistical inference, right? And again, you've probably seen this before. This is our story about hypothesis testing, right? And so we're going to lay out the whole structure of this system, but more than likely it's something you've seen before. We can again apply this to a business context, right? We can think about a company who does call center training, and we've got some data that's posted on Moodle in terms of how long it takes to complete a call. And so the motivation behind this, right, is that you're running a call center, and then they adopt this new training, right? So between 2017 and 2018, in that little gap, they have some new training. And so the question they might want to ask is, yeah, was this training effective? Was it worth it, right? They want to consider what was the cost of their training, and then they want to figure out, is there a benefit, right? Is there an actual benefit to the training that they did in 2018? And is that evidence convincing? And so we can bring up that data and talk through that real briefly. Very briefly, just to explore this. So this is the data from 2017, and notice that we've got a bunch of IDs, so we've got a bunch of observations, right? So notice that this is 1,000 observations. It's not every single call that was made in 2017. Rather, it was a random sample that was drawn from 2017. That's key, right? We're not looking at the whole population. We're looking at a sample. And so what we've got is we've got the different call times in seconds of all of those different calls, and then to the right we've got some descriptive statistics, right? The average call time was 143 seconds. But 143 was the average, right? You could think about this to the right as a histogram that shows the empirical distribution of all of these calls. What's the expected value of this It's not a normal distribution, right? Think about the 4 criteria of a normal distribution, and this doesn't fit it, but still, right? Could you calculate what the expected value is of this distribution? That's what this average is. The sample is going to be closely representing, right? So it looks like on average, these calls took 143 seconds, but some took longer, some took shorter, but on average in 2017, before the training, the average call time was 143 seconds. And then in 2018, it changed like this, right? So again, we've got not all of our observations, but we've got a random sampling. To scroll to the bottom of this list, notice this list, a lot smaller. We've got the count, only 40 observations in this sample, right? And the sample in 2018 had that the average call time was down to 141.3. But notice, look at this distribution, right? That it's got some are above, some are below, on average 141. So the question is, right? Did the training seem to lower the call time? Well, it's a lower number, but is that just random statistical randomness? Or was it actually that the training did something to reduce call time? This number is smaller. Is it smaller enough to convince you that indeed the training did something important? Again, to reemphasize, the main question that hypothesis testing lets us look at is, yep, the number looked smaller, but was it convincing, right? Is that number different enough to really convince you that this training did something that actually lowered call time and it wasn't just some random variation in it? That's what hypothesis testing does. So again, some of this you've seen before. Hypothesis testing, right? We're drawing inference about 2 contrasting propositions, right? And so you would probably recall in an earlier statistics class considering a null and an alternative hypothesis. So together, what the null and the alternative have to do is they have to be a mutually exclusive, completely exhaustive set of propositions, right? And so what does that mean? Again, mutually exclusive. You cannot have it be both of these things. It has to be one or the other. Mutually exclusive and also completely exhaustive. They have to cover all possible outcomes, right? So what do? In our null hypothesis, it's where we put our existing theory or our existing system of belief that we accept as valid until we've got enough evidence to convince us of the contrary, right? And so this often gets presented as, oh, this is the most clear-cut thing in the world in terms of what you should put as your null and what you should put as your alternative. But really, right, the thing to remember is this null hypothesis, it's what we're going to believe to be true until the data convinces us otherwise. And you could think about, right, different alternatives for the way that we could approach what we put in the null, what we're putting in the null is the thing that we're going to assume to be true unless the data convinces us otherwise, right? And so the alternative hypothesis is the complement to the null hypothesis. So it represents the thing that the data has to convince us of. And so one of the classic examples that I think of, right, is in a criminal trial, right? In the US, when we do criminal trials, we can think about where do we put the burden of proof, right? Do we put the burden of proof on people when they're in a criminal trial to prove that they are innocent or prove that they are guilty? Right? Fundamentally, in the U.S., and hopefully you've got some not personal background, but some knowledge of this, right? It's in pop culture all the time and those kinds of things. But right, when we do a court of law, what are we doing? Are we assuming automatically? Is our default belief that people are innocent and we need the evidence to convince us that they're guilty, or is the default perspective in the court in a criminal court that we think everyone who comes through is guilty and we need to provide evidence to convince us that they're innocent, right? So my formal question is, how would you write down the null and alternative hypothesis for the US criminal system? What should go in the null hypothesis? That is our default perspective, and then what should go in the alternative? All right, so hopefully you spent a little bit of time thinking about that and generated an answer. What do we do in the U.S., right? We've got this saying, innocent until proven guilty, right? So if we have innocent until proven guilty, until the data convinces a jury or a judge that someone is guilty, then what are we assuming should be the null hypothesis? What should our default belief system be about someone in the U.S. criminal court? Yeah, that should be the not guilty, right? And what we are trying to have the data convince us of, that's what goes in the alternative hypothesis, that's someone guilty. Another way that we could think about this, right, is I often think about people cheating on a test, right? Think about whether I made my null to be that everyone is cheating on the test or that no one is cheating on the test, right? Think about what that means in terms of what kind of evidence I'd be looking at to convince me that I was that my null was incorrect. And that's really what hypothesis testing is doing, right? It's a structure in place where we've got our existing set of beliefs, and hopefully those are come from a good rational place, and then we're looking at data to convince us that those beliefs are wrong, right? So again, the way that we state things when we turn and look at data is always in terms of this null hypothesis, right? So we're going to turn and we're going to look at some data. I've been using the word evidence and data interchangeably here, right? But we can turn and we can look at some evidence, we can turn and look at some data, and then we make a statement relative to whatever that null hypothesis is. We either reject the null hypothesis, meaning that our sample evidence sufficiently and convincingly convinces us that the null is incorrect and that this alternative is what our decision is, or we just simply can't find enough evidence that the sample evidence does not provide enough evidence to convincingly have us support the alternative, right? We can, and again, you may have seen different lists of this in an earlier statistics class, but these are the ones that I'm going to follow, right? So in general, right, when we're doing hypothesis testing, there's a couple of steps usually to the process. Number one, identify the population parameters of interest and formulate the hypothesis to test, right? So we got to know what's the question that we're asking about. Fundamentally, the question that we're asking about is going to show up in this null and alternative hypothesis. It tends to be that the claims we want to investigate, we tend to be skeptical of claims, and so they tend to be the things that go in the alternative hypothesis, right? But we got to make sure that we've articulated what's the question of interest that we're looking at, and that we've clearly understood what our default perspective is and what we're putting the burden of proof on demonstrating. And that burden of proof on what we're demonstrating is the thing that goes in the alternative hypothesis, right? So we got to do this. We got to be able to write down what the null and the alternative is, and everything connected with that. Most of the times when we're doing population parameters, we're going to be asking a question about the average of something. And not always. Later in this class, we're going to look at other kinds of hypotheses tests, and we could in further classes, right? But for the most part, we're going to be asking questions about averages. If I go back to that data, right, the question that I posed to motivate this was about the average call time, right? The average call time. But notice, what was I doing? I was not asking my null and alternative hypothesis about X bar. No, I wasn't. Instead, when we frame a null and alternative hypothesis, it should be not in terms of a sample, but in terms of a population parameter, right? So you should be using μ's for your null and alternative hypothesis about the means. Number 2, we got to select what's called the level of significance. This is the alpha that you may recall from hypothesis testing. Oh boy, what is an alpha? This is a little complicated, but what we can say is that alpha is the probability of committing a type 1 error. Of a type 1 error. If conditional on the null being correct. Right? So whatever we have in our null hypothesis, if that were correct, then, right, there's a certain probability associated with the null being correct, but randomly, through statistical randomness, we observe a value that convinces us that that null is incorrect. That would be committing a type 1 error. The probability that we feel comfortable committing a type 1 error is what we call the alpha. Oh boy, that was a lot of words. Recall, right, that a type 1 error is coming up with a false hypothesis or a false or a correct hypothesis. I just realized I jumped a little bit ahead of myself, and so I've laid all this out, and it's useful to start getting comfortable with this terminology. But let's go back. The level of significance defines the risk of drawing an incorrect conclusion when the assumed hypothesis is actually true. All right, so what do those words actually mean? Right, so we've got when the assumed hypothesis is, do you remember what do we assume to be the default correct until the evidence convinces us otherwise? That's the null, right? So it's when the null hypothesis is actually true, but we draw an incorrect conclusion, right? So a type 1 error is the null was actually true, but the data led us to believe that it was not true. The data led us to believe what was in the alternative when the null was actually true. So again, if we go back to our story about the US criminal system, right? What would be an example of a type 1 error? What would be drawing the incorrect inference when the assumed hypothesis is true? What would it mean in your own words if we commit a type 1 error? It means that the null was true, but we found evidence to convince us of this. In your own words, describe what that would look like to commit a type 1 error in the US criminal system. It is always possible, right? Because we are dealing with uncertainty here. We're not looking at a population. We're going to look at a sample to make some inference. And it's possible that the inference of our individual sample might have us believe that this null hypothesis is not correct. Our sample might be evidence that convinces us that the alternative is correct, even though it might not be. That's what a type 1 error is. The level of significance is our probability that we're comfortable with committing that type of type 1 error, right? So once we have our level of significance, then we can think about the underlying distribution of our population parameter. And again, from that central limit theorem, we know that the distribution of sample averages looks like a normal distribution, right? And it changes the variation in a predictable way. And so most of the time, right, we're going to be looking at a normal distribution. Not always, but most of the time we're going to be looking at a normal distribution. Our level of significance is the probability that our null hypothesis, this null average, what we believe to be true in the null hypothesis, is not correct, right? And so there's a certain level of comfort that we have with committing a type 1 error. Whatever that level of significance is, our comfort with committing a type 1 error is going to translate on this graph to certain regions, right? And so the evidence, if it's beyond a certain point, will convince us that the alternative should be followed, even if it's incorrect, right? Again, so that's step 3 is really think about what's the structure that you're going to use to try to evaluate a decision. Step 4, turn and look at some data, right? So step 4 is the first time that data actually falls into this. Up to this, what we're doing is we are putting in place a structure that we're going to use to evaluate something we don't know. And it's only at that point that we turn and look at data, right? And so you could think about, hey, that's a good way for science to be structured, right? Where we think about how we would structure the answer and how we would interpret information before we go out and collect information to find out what the decision should be, right? And we could also make an argument that that's a good way to do public policy as well, right? And so once we've got our data, then it's just a matter of take that data and apply the decision rule from it and figure out whether or not you have been convinced that the null is not correct, or whether the alternative, the data convinces you that the alternative is correct. So an alternative way that I've seen this stated, right, this procedure, form your question, decide what a compelling argument is, look at evidence, draw a conclusion. That seems like a good form of critical thinking. Most of the time, what we're going to be looking at is a single population parameter. And again, most often the mean. So the mean of the population, those are going to be the mu's. And so that's the notation that you're going to want to use in your null and alternative hypothesis for most of the things that we're going to consider. So a question we could ask, right? If we have a claim that we want to investigate, that say the claim we want to investigate is that the average income in one of these high growth counties is greater than $60,000, right? If that's the claim that we want to investigate, I'm going to want the data to convince me that that claim is correct, right? I don't want to automatically assume that that claim about incomes being greater than $60,000 in a high income growth county, I don't want to believe that claim unless the data convinces me that it's correct, right? The thing, and again, that's where what I'm describing with my words is where I'm putting the burden of proof on the data to convince me of. That's the thing that should be going in the alternative, right? And so again, we talk about a population parameter as a mu, and in this case, I'm talking about the average income in a high growth county being greater than $60,000. So in this case, what should be the null hypothesis? Recall that the null hypothesis and the alternative hypothesis, they're complements to each other, right? The list has to be mutually exclusive and completely exhaustive. So there can't be any overlap, and it has to cover all possible values. So if I've got that average income is greater than 60,000 is the claim, what's the opposite of something being greater than 60,000? The opposite is that it is less than or equal to 60,000, right? And so these two together form a mutually exclusive pair, right? You cannot have both, and it covers all possibilities, right? But the question that you may remember from an earlier statistics class, would this be an example of a one or a two-tailed hypothesis test, right? This is an example of a one-tailed test, right? A two-tailed test has in the null hypothesis an equality, and in the alternative, it has an not equal. Whereas these one-tailed tests have these inequalities, or this, right? One of those two things, right? And so again, this two-tailed test, when I do a two-tailed test, you may recall that the picture of the distribution of what's in the null hypothesis looks something like this, where you're shading in both sides, right? If it's a two-tailed test, then you shade in two tails. That's pretty easy to remember, right? A one-tailed test is going to shade in one of the two tails. Do you recall for this claim, is it this one or this one? Right, and so again, you can think about what are we requiring the data or the evidence to convince us of? What we're we're requiring the data to convince us of is that these incomes are indeed more than 60,000, right? We'd need high average income to convince us of this claim. We need the data to fall somewhere to the right and be a high level of income. So it's this one on the right, right? This one that has the shaded the shaded tail to the right. So another way that when I've taught this class, one of the heuristics that people use is this looks like it's an arrow that's pointing to the right, and so you shade in the one to the right. Again, it works. I would prefer that you thought about it in terms of the burden of the evidence to convince you, but if you also want to think that it's pointing to the right, and so that's what you should shade in, that also works as well. Okay, so we had described this earlier about what the null and alternative are presented as, and what the evidence convinces us of. We are going to believe our default belief about the world is going to be in our null hypothesis, and we're looking for the evidence to convince us that the alternative is correct. We're putting the burden of proof on the evidence to convince us of what's in the claim in the alternative hypothesis, right? But this is, there's a difference between what the underlying truth is of the situation and what that evidence is telling us, right? And you could think about, again, if we go back to that story about the U.S. criminal, you've heard examples of people who have been guilty, but the jury found them not guilty, right? And there's also examples of people who were found guilty who it later showed that they were in fact innocent, right? And so you've got sometimes the system in place looks at the evidence and it draws a conclusion from the evidence that is not in line with the underlying truth. So here we go. This is one way that we can think about this relationship between the underlying truth and what the evidence points to, what the evidence convinces us of. If the underlying truth of the situation was indeed that null hypothesis was correct, and the evidence tells us that the null should not be rejected, no problem, right? The evidence was pointing you to the same thing as what the underlying truth was. Alternatively, right? What if the null hypothesis is actually not true? What if the thing that we are investigating in the alternative hypothesis is actually true, and the evidence tells us that null, you should reject that null. In the case that the null is not true and we reject it, again, no problem. That's not a problem whatsoever, right? The problem comes in these off diagonals, right? And so these off diagonals, we've already talked about one of these two off diagonals, a type 1 error, right? In a type 1 error, the null was actually true, right? Whatever we had in the null is actually the underlying truth of the situation. However, the evidence suggests, no, reject that null. We got it wrong. This process led us to the wrong place. The evidence led us to believe something that was incorrect. Specifically, the null was true, and we were led to believe it was not true. That's what a type 1 error is. And again, we refer to this, the probability of our comfort with that, as the alpha, or the level of significance. A type 2 error is still an error, right? But it's an error in a different configuration, right? Whereas the null, let's do that in a different color. The null is actually wrong, right? The thing that we believed as our default perspective about the world is wrong. The alternative, the claim that we're investigating, is actually what the truth is. However, the evidence convinces us not to reject the null. That's a mistake, but that's a different kind of mistake, right? That's a type 2 error. So again, if we think about in the US system, we've got an innocent man who gets sent to jail or a guilty man who goes free. Which of those two is the type 1 error? Some additional language we can add, right? So 1 minus alpha, we can refer to that as the confidence coefficient, and 1 minus beta, that's the power of the test, and we'll come back to this later. Beta is the probability of committing a type 2 error. There's one other story that I want to tell real quick in terms of this type 1 and type 2 error, and it has to do with the terminology of false positive and a false negative. Remember that what hypothesis testing is doing, right? When we carry out these hypothesis tests, what are we doing? We are investigating a claim. And so we are carrying out a test. And so if we have a positive test for something, it means we found evidence to convince us of whatever the claim was, right? So if that test is positive, it means whatever we found in the alternative, the evidence convinced us of it. If the evidence convinces us that whatever's in the alternative is correct, but that inference we drew from the data is false, what are we describing here? A type 1 or type 2 error, right? A type 1 error is when the evidence convinces us to reject the null hypothesis. The evidence convinces us that what's in the alternative is correct, when in fact it is not. We refer to that as a false positive of the test, right? So a false negative is the opposite, right? It's when our test comes out negative, right? A hypothesis test is testing for what, does the data convince us of what is in the alternative is correct. If the data does not convince us that what is in the alternative is correct, then the data is leading us to believe that the null should not be rejected. But if it's false, that means we shouldn't have not rejected the null hypothesis. Double negative there, right? In essence, that's a type 2 error though, right? If the if the evidence convinces us don't reject the null, but in fact the null should have been rejected, that's called a false negative, right? So I like these terms a little bit better than type 1 and type 2, but again, you see them a lot in statistics. I think these are a little bit more intuitive, but you should also learn both of those. And real quick, I did a Google search on this to bring up the image that's one of my favorite images to help remind the difference between a type 1 error and a type 2 error. Right, so again, a type 1 error, we just described that. That's a false positive. So for example, a doctor telling this guy that he's pregnant. That's a type 1 error. This doctor telling this woman, who is very clearly pregnant, that she's not pregnant. That's an example of a type 2 error or a false negative, right? So again, I like it because I think it's funny. But think about for a second, what is the null and alternative hypothesis that we're using to carry out, to describe these type 1, type 2 error, false positive, false negatives, right? You can think about what are we naturally going to believe about something, and then what do we need the evidence to convince us of? What are we putting in our null? What are we putting in our alternative to generate this kind of structure? We can hop back right here. A pregnancy test, what is it testing for? It's testing for pregnancy. So that is what should go in the alternative, right? That's what the test is after. That thing that we're having the data convince us of is what should go in the alternative. And so you could think not pregnant is what should go in the null of that, right? And so we carry out this, we've often got to think about our test statistic, right? We've got our mu is going to be the hypothesized value that goes in our null hypothesis. We in order to carry out the test, we need to have what we call a test statistic, right? That tells us about the value of our evidence in relation to the way we've structured our decision rule. Oof, lots of words. But that's just saying, if we have a one sample test for means, which is what we're going to focus on initially, we've got two different versions of this test statistic. One, when our sigma is known, and another when our sigma is unknown. This should sound a little bit familiar after we talked about these 90% confidence intervals, right? That we've got same kind of thing. Are we going to use a z value or are we going to use a t value, right? And again, what does a z value distribution look like? A z value distribution is just a standard normal distribution where it's centered around 0 and it's symmetric and it goes out infinity in both directions and it perfectly follows the empirical rule, and a standard normal distribution has the standard deviation set to normalized to 1. Right? If that's my z distribution, that should look very familiar to you. If you recall, right, we use our z distribution when we know what the underlying variation in our data is, or in our population is. If we don't know what the underlying variation in our population is, then we should use the t-distribution that captures a little bit more uncertainty. Again, what does a t-distribution look like? Maybe something like this, where it's just got a little bit more uncertainty built into the tails. It's got a little bit fatter tails to adjust for that additional amount of unknown of not knowing what the population spread of the variation is. But notice, the structure of these things look very, very, very similar, right? Whereas in the numerator, we're looking at the sample average minus whatever we thought the null to be, and we divide by the standard deviation divided by the square root of the number of observations. It's just, are we using the known population standard deviation, or instead, if we don't know what the population standard deviation is, we go ahead and use the sample standard deviation, right? So again, all of that just structuring, this structures how we do the t-statistic. In a second, we'll talk about what would that look like in Excel. And again, we want to make sure that we've got our picture set up. So we got to know, is our test statistic a z or a t distribution? Either way, it's going to look something like that. And we've got our rejection regions, right? And so given our level of significance, which again, recall, your level of significance, your alpha, is the probability that you're comfortable with committing a type 1 error. Once we know how comfortable you are in screwing things up and committing that type 1 error, then we can define what we call the critical values. And they're the value of z or t such that the probability of the alpha is outside of those. This is a classic two-tailed test. And again, some of this should be coming back to you from a basic statistics class, right? If our alpha is 0.05, we need to take that probability of committing a type 1 error, and if we have a two-tailed test, we take that probability and we split it in half, right? So in that case, 0.025. So we would want this probability over here to be 0.025 and this probability over here to be 0.025. That's saying that we're going to assume the null to be correct. And we really need the evidence to very, very strongly convince us that the data is telling us that the null should be rejected. We could get it wrong. And this is the small probability that we get it wrong. That's the basic structure about setting up critical values. And again, we'll walk through an example with that. An alternative way to draw a conclusion about the null and alternative hypothesis is we can turn and we can look at the data, right? And if we look at the data, it will generate our test statistic is going to generate a value of our test statistic, and we could take that value of the test statistic and we could figure out where does that value of z or t from the data fall in this distribution, and we could calculate the probability associated with getting that level of test statistic when the null is true, and that probability is what we'd refer to as the p-value. Again, this p-value, it's got a big mouthful of an explanation, right? The p-value is the probability of observing the z or t test statistic when the null hypothesis was true, right? Oftentimes, you'll see in an intro stats class, this gets referred to as the probability of the null hypothesis being correct. That's not correct, right? That is an incorrect interpretation. It's a useful way to think about that number as a first pass, but a better explanation, and I'm putting better in quotes because it is a mouthful, a better explanation of what a p-value is it is the probability of observing that z or t statistic from the data given, conditional on, the null hypothesis being true. As a side note, there has absolutely, in social science research, been this recent reaction to p-values and trying to rethink the way that we explain and use these things, because oftentimes they get misinterpreted. And so, again, we want to be a little bit more careful going forward about the way we talk about the p-values. But in general, right, the p-value is going to tell us something. What we can do is we can take our value of alpha, which is the probability that we commit a type 1 error, and if we compare our value of alpha to the p-value that generates the z or t value, conditional on the null hypothesis being correct, we've got this basic relationship, right? That if our p-value is less than the alpha, it means that our test statistics are way out here in the tail, and that we should reject the null hypothesis, right? And so, again, you may have seen this from either direction, right? Either first calculating the z or t and putting it on the distribution, or alternatively taking the value of the z or t and calculating a probability and then comparing it to an alpha. Either one of those is going to put you to the same place in terms of your decision rule about what you do with your null or alternative hypothesis. That's all theoretical. What I want to do next is I want to turn to a couple of different examples and walk through what it would look like carrying out this process and how we could do it in Excel.